This is a re-recording of our presentation, Expert Viewers' Preferences for Higher Frame Rate 3D Film, that was presented at Stereoscopic Displays and Applications in San Francisco in February of 2017. The presentation was not recorded at the time, so we re-recorded it for inclusion in the video proceedings. This work was done in collaboration with my colleague at York University, Laurie Wilcox, Roy Anthony from Christie Digital, and John Helliker and Bert Dunk from Sheridan College. In the early days of film and cinema, the frame rate was determined by the cranking speed used by the projectionist. This gave acceptable motion and was suitable for the silent error films. However, there was considerable variation between theater and theater, and even within a theater, as the projectionist varied in his cranking speed. With the transition to talkies, we needed to fix the frame rate at a constant rate. This is because with sound encoded on film, we didn't want the sound speeding up and slowing down as the frame rate varied. This constant frame rate then needed to be set, and setting it was a bit of a challenge because there's a trade-off between image quality. As we increase the frame rate, we get better quality, but we would also have a trade-off with economics. As we increase the frame rate, we need more film, increasing the cost, increasing the complexity, and increasing the chance that we need to change film reels in the middle of a movie and have increased intermissions. So based on these factors and current practice at the time, the industry standardized on 24 frames per second, and we've been stuck with that ever since. This decision has had a huge impact on the expectations of what people should see when they go to the movie theater. These aesthetics and expectations have been termed the film look in order to distinguish them from, say, the expectations that you get when watching television or watching video. The film look includes aspects such as depth of field, dynamic range, and film grain that affect the static image, but also temporal aspects such as frame rate and shutter angle. Moving to digital cinema allows us the opportunity to break free of the straitjacket of 24 frames per second and consider higher frame rates and even variable frame rates, where we may want to fix the frame rate and set it according to the needs of a particular shot or particular film. Why do we care? Well, we care because the frame rate has measurable and significant impacts on the viewer. For instance, at the most basic, if we're showing an image and we're flashing it, if we don't flash it fast enough, we'll get a sense of flicker, where it'll appear to come on and off, or dim and flicker, like a bad fluorescent light. Turns out 24 frames per second is not fast enough to avoid flicker, and if we have a 24 frame per second movie, we need to show each image multiple times in order to avoid flicker. In practice in stereoscopic film, we will show each image 3 times for each eye, so we get 72 hertz or 144 hertz flash rate for a 24 frame per second per each eye frame rate. If we don't have a high enough frame rate, we will also get impacts on motion smoothness and artifacts such as jitter. Cinematographers know this, and they know how fast they can move the camera based on rules of thumbs and experience in a 24 frame per second movie without getting into trouble. So this basically constrains the cinematographer. We also get artifacts such as aliasing. The classic example of this is the wagon wheel. As the wagon wheel speeds up, it'll appear to slow down as it approaches the Nyquist rate of the camera. Then it'll appear to reverse, and so on, and we'll get artifacts. This is easy to see in these classic effects, but it can occur anywhere in the image. And finally, we get motion blur, which is indirectly related to frame rate. Motion blur occurs because during the exposure, the image can move on the camera, image of a fast-moving object, or if the camera's moving, and this will smear the image and blur it. The length of time the exposure, the image is exposed, will determine the amount of blur, and this is indirectly related to frame rate because typically the exposure time varies with the frame rate. Most of these artifacts can be considered in terms of their spectral content and how sensitive we are to these variations in time and space. The perceptual consequences of these factors can be demonstrated and illustrated using tools such as the spatial-temporal contrast sensitivity function. At the meeting, we showed a stereoscopic version of this graph, but here we show Watson's original. The contrast sensitivity function plots the sensitivity of an observer to various types of stimuli. In this case, it shows it as a function of temporal frequency and spatial frequency. So these are shown on the two axes at the bottom of the graph. So one shows temporal frequency in hertz. So this is the variation at a given image over time. So as it goes from dark to light, dark to light, dark to light, how fast and how frequent those changes are in terms of cycles per second. The other axis shows spatial frequency, or variation over space. So basically, as a pattern changes and gets darker and lighter as we go across a texture, say for example. The higher the spatial frequency, the higher the detail in the image. Okay, so for any combination of this, we can ask how sensitive someone is, and that's what's plotted on the vertical axis. So the higher the plot, the more sensitive people are. So we can see that it's a complex function, and it dips at low frequencies and so on. But you can also see that at high frequencies, there becomes a limit where you can no longer see it, no matter how intense the image is, how high contrast the image is. So beyond this window of visibility, we should not be able to see artifacts. So Watson defined the window of visibility, which is a conceptual model of this that basically illustrates if an artifact arises and it falls outside of this window of visibility, then there's no way that observers could see it. If it falls within the window of visibility, then it depends on the contrast and other factors whether it will be seen. But at least we know whether something will be seen or not based on the window of visibility. Tools such as the window of visibility then can describe whether an artifact is visible or not. And based on these, we can objectively say that higher frame rates improve resilience to motion artifacts. This is also true in stereoscopic domain, and Hoffman et al. Showed that temporal disparity in time sequential stereoscopic 3D is reduced as frame rate increases. These effects can be predicted and sensitivity can be measured, and we can say that objectively, all things being equal, things are better at higher frame rates. However, things are not always equal. For instance, sensitivity does not necessarily predict preference. We may prefer some artifacts over the other. For instance, we may prefer a softer image with some motion blur over a staccato appearance in a motion picture. And if you look at something like this pointillist painting, people may prefer it over the original, or at least the scene that's portrayed. However, this is an aesthetic judgment. These aesthetic judgments, of course, are very idiosyncratic and particular to individual people. So we looked at these issues in a previous study in 2015 where we reported preferences for different frame rates with a naive film audience. And we found with this particular audience that there was a clear preference for higher frame rate for both judgments of realism and judgments of image quality. Participants were predominantly young adults though, and as such they had a lot of experience with playing video games, watching HD video, and so on. Lots of experience with higher frame rate content. So we asked whether the same results would be found if we had an audience that was invested in the film look, say for instance film industry professionals. In order to study this, we needed some content. We wanted our content to be as cinematic as possible, so we used professional equipment and we used the standard procedures for production and post-production to take great care to make sure that individual shots were as repeatable as possible from one condition to another condition. So as we varied frame rate or as we varied shutter angle. All the scenes we shot were outdoor, shot on location by professional crew, and they were cinematic both in content and quality. We used a professional crew, professional actors, trained actors, so that we get repeatability and have as good a comparison between different frame rates as possible for the same shot. The shots we used were very different in their cinematic quality in terms of the type of image that they were. At the actual Stereoscopic Displays and Applications meeting, we showed these in stereoscopic 3D. We don't have a stereoscopic display, so we're just going to describe them to you here. The first was a very dramatic shot. A woman walking through the grass, brushing the grass was blowing in the wind, and then she sat down at a picnic table in a mild breeze. The next one was a difficult shot. It was a woman walking a bicycle behind the bars of a metal fence. There's all kinds of issues with aliasing and other artifacts in this particular clip. And finally, the last one was a action shot. A martial artist, a world-class Canadian national champion, wushu warrior, did a sword routine. She was very, very disciplined, and the routine was very repeatable and very impressive in terms of the speed of the motion. All three of these shots were then filmed under three different frame rates, 24, 60, and 48 frames per second. and at 3 different shutter angles, 180, 270, 358. This gave 27 different conditions, different shots that we could compare in pairwise comparisons. We wanted the display, the projection, to be as cinematic as possible as well, so we replicated theater settings. We used a large film screen, we used a cinema projector, commercial cinema projector, we used commercial Real D circular polarizing glasses like we have in North American theaters, and finally we set the white level of the screen to 16 candelas per meter squared through the filters in order to match IS&T standards. So it was set up like a high quality stereoscopic 3D cinema. We seated the observers similarly in rows with 1 meter separation. In this study, we used 56 observers who are all industry professionals. So these were colorists, editors, people, cinematographers, people that were used to judging, grading, and creating high quality film look and high quality cinema. They were all screened for stereopsis, so they could see 3D depth in stereoscopic films, and they had normal acuity, at least wearing their glasses. We compared these then with 51 observers from the previous study who were young adults screened in the same way. So what did we ask them to do? On each trial, they watched a pair of film clips. The film clips were the exact same shot, so it was, the Wushu Warrior twice, or the bike shot under 2 different conditions. And between the 2 different versions of the clip, there's a brief dark interval. So they should be identical in terms of content. However, they did vary in terms of frame rate or shutter angle, or a combination of frame rate and shutter angle. So the observers were to pay attention to both clips and then rate them on the relative preference on 5 different characteristics: realism, motion smoothness, blur, quality of depth, and overall quality. They used a 5-point scale going from strongly preferred clip 1 to strongly preferred clip 2. Okay, so they made a preference rating between these 2 clips. It turns out to do all the comparisons between all possible pairs would take many, many hours. So we needed to focus down on key variables. To do this, we considered 22 paired comparisons to evaluate these. The first one was the frame rate. So we're interested in whether 24, 48, and 60 frames per second content differed in terms of its perceived quality. So we compared 24 and 48, 24 and 60, and 48 and 60, all possible comparisons. But we only did this for the bike and the warrior shots, and we did it at 180-degree shutter angle to reduce the number of comparisons. So this allowed us to study the effect of frame rate. Similarly, we're interested in the effects of shutter angle. So once again, shutter angle, this comes from the days when there was a mechanical shutter, and it really refers to the amount of time, the proportion of the frame interval that the image is exposed. So the frame interval is done in degrees, so 360 degrees would be a complete frame interval. So if we have a 180-degree shutter angle, this is basically half the frame. If we had a 270-degree shutter angle, this would be 3/4 of the frame. And if we had a 358, this would be almost the entire frame. Okay, so these are the 3 that we compared, and we did this for all shots, but fixed at 60 frames per second. Finally, we're interested in the exposure. So let's say motion blur matters, how long the image is exposed in terms of time rather than in terms of angle. So it turns out that if you take 24 frames per second at 180 degrees, this means that half of the frame is exposed, and a frame is 1/24, so you get an exposure of 1/48. Well, it turns out if you have 48 frames, but you expose it for the entire time, you also have an exposure of 1/48. So basically 24 frames per second, 180, and 48 frames per second, 358, are equivalent in terms of exposure. So we wanted these 2 to be compared. We also threw in 48 frames per second, 180, because there we could compare with 24 frames per second, 180 to see the effect of frame rate, or we could compare with 48 frames per second, 358 to see the effect of shutter angle with this content. And we did this for all shots, all 3 shots. Okay, here's the sort of data that we got. So remember, on every trial, subjects were instructed to pay attention to the 2 clips and then compare them relative preference. So they could either strongly prefer clip 1, have no preference, or prefer clip 2, for instance. So this graph then shows along the bottom, it shows the 5 different aspects that we're measuring: realism, motion smoothness, blur, quality of depth, and overall preference. And then the three different bars are the three different comparisons. So the blue compares 24 frames per second versus 48 frames per second, once again of the same clip. The gray compares 24 frames per second versus 60 frames per second. And finally, the white compares 48 frames per second versus 60. Okay, so along the y-axis, we have the preference. So this is coded as follows. If we get a 2, so highly up here, this means that the observer strongly preferred the higher frame rate. Now the order was always random, but we've reordered it so that 2 always indicates a preference for the higher frame rate, whether it came first or second in the pair. 1 indicates a more modest preference for higher frame rate. 0 indicates no preference or neutral. -1 indicates a preference for the lower frame rate. And -2 is not shown here, but that would indicate a strong preference for lower frame rate. So we can see here that all of the data is above the line, or most of the data is above the line, indicating a preference for the higher frame rate. And this is especially true for the blue bars, which indicate 24 versus 48. So observers preferred 48 frame per second content over equivalent 24 frame per second content. And the gray bars indicate that observers preferred 60 frame per second content over equivalent 24 frame per second content. Where it falls apart a little bit is for the 48 versus 60, where there's no strong preference and things are mostly around neutral. Okay, so I'm going to take exactly the same data and shrink it down and put it on the left-hand side for the next graph. Okay, so on the left-hand side of the graph, we have exactly the same data we had before. That was for the expert viewers in this particular study. And on the right-hand side, we have the equivalent data for our naive observers in our previous study. And you can see the overall trends are very similar. A preference for the higher frame rate, 48 over 24 and 60 over 24, and little or no preference for 60 over 48. Okay, and this is averaged across the clips. So we found a significant and reliable preference in both groups for 48 frames per second over 24 and 60 frames per second over 24 frame per second content. For overall preference, observers in both expert and naive groups preferred the warrior clip, though, when presented at 60 frames per second compared to 48 frames per second. So whether 60 versus 48 made a difference depended on the content. For the bite clip, there was no difference, but for the faster action sequence, the warrior clip, both groups preferred 60 frames per second over 48 frames per second. Okay, so what about our second variable, the shutter angle? Well, this will be a quick one because essentially if you look at the shutter angle, you notice that all of the data is clustered around the 0. So the 0, as you recall, is no preference. So basically, regardless of whether it was 180 versus 270, 180 versus 358, or 270 versus 358, our viewers had no preference for different shutter angles, averaged across the clips. So to summarize then, no effect of the shutter angle on preference. And this was also true for our naive group. So for neither the naive group nor the expert group had a preference. There was no difference this time between the clips. It didn't matter which clip we showed. And importantly, there was no evidence of a bimodal distribution of responses. So we had predicted that perhaps we would get a group of people that really liked the film look, and a group of people that really liked the sharp look, and then we'd have a dichotomy where we get two groups of responses. But instead, we found that the response was unimodal and around the neutral point. So no indication that we had two groups of people. What about this last comparison, this exposure comparison that we want to do? So in this case, we have two comparisons that are of primary interest. The first one is this gray one here, which compares 24-180 versus 48-358. Recall that these two conditions have equivalent exposure duration. So in terms of motion blur or exposure, if that was the primary factor, we'd expect that since they're equivalent, there'd be no difference between these two, and we get data around 0. But as we can see, they're all significantly positive, indicating that even when exposure is equated, we have a strong preference for the higher frame rate. The second comparison of interest is this one, which is 48-180 versus 48-358. This is again showing the shutter angle effect. And here we see that for this particular content, we have a small preference for 358-degree shutter. So at 48 frames per second, we have a small preference for a longer shutter or more blur. Okay, so and finally the pink one shows the frame rate effect, indicating that at 180-degree shutter, we prefer to see 48 frames per second over 24 frames per second. Okay, so the other thing I didn't mention there is we confirmed a significant effect of frame rate. We preferred 48 frame per second content over 24 frame per second content, regardless of shutter angle. And we found some weak preference for longer exposures. This is at the 48 frames per second, where the experts preferred the larger shutter angle, particularly for the rapid action warrior clip. This was a little bit different than our naive group, who actually preferred the larger shutter angle for the picnic clip for motion smoothness and overall preference. So the more dramatic shot for the naive group. So we did have some evidence for a preference for longer exposure, but it was not necessarily consistent for clip. So in conclusion then, we've confirmed that we have a clear preference for higher frame rates regardless of the type of content. A relatively little difference between 48 and 60 frames per second compared to 24 to 48. And when we did see this benefit at 60 frames per second, it was in the warrior shot with very rapid motion. And in general, this preference for higher frame rates is consistent with other studies in simulation and gaming. Also, recall that frame rate and flash protocol was shown by Hoffman et al. To impact instantaneous disparity, and higher frame rate should give you less disparity artifacts. While we did see improvements in depth quality with higher frame rate in this study, these improvements were actually smaller than for all the other judgments. So we think that actually the preferences are not primarily driven by stereoscopic 3D effects or improved stereoscopic 3D depth. However, it's important to note that we used constant stereography. All the shots were shot with stereography appropriate for the shot, and we didn't vary these variables systematically, so there may be some interactions between stereoscopic parameters and frame rate. Finally, we had a preference for high frame rate film for both realism and quality. This may run counter to some criticism that's been leveled against high frame rate film, that it's too real. For instance, some of the reviews of The Hobbit. Okay. However, we don't think this is too much of a discrepancy. Recall that our content was filmed on location with natural makeup. Under these conditions, increasing realism should increase the quality of the image. However, in other cases, it may paradoxically give away a movie set. For instance, if you've got props or fantastical makeup, increasing realism may actually give away the fact that what you're looking at is fake, not what's trying to be portrayed. In general, our results generalize from young adults accustomed to video games to experts invested in the film look. So regardless of whether you're a young adult raised on playing video games, or whether you're a film industry expert whose day job is to produce high quality film and has a lot of time and effort and other investment in the film look, high frame rates offer potential for increased image quality. Thank you.